In this video, we will talk about how to find the area between two curves. So I want to motivate this with a picture. So let's draw some axes. So I'll have a y-axis and an x-axis, and then I'll have some curve, which I'll call y equals f of x, and we'll also have some other curve below that, which I'll call, so maybe it looks something like this. And this curve I'll call I'll call this y equals g of x. And let's say that there's some interval from a to b, and we are trying to find the area between these two curves over this interval from a to b. So we want to find the area between f and g over this interval from a to b. Okay, so our idea for computing this is going to be really similar to how we first computed the area between a curve and the x-axis, which is to use rectangles and then evaluate a limit of a Riemann sum. So let's use some rectangles to first approximate the area, and then use a Riemann sum and take the limit of it to make it an exact area. Okay, so I'm going to draw a picture of this, and then we'll describe it with a formula. So very similarly to what we did before with just finding the area between the curve and the x-axis, what we can do is we'll split up the interval from a to b into sub-intervals. So I'm just going to draw a few tick marks here. So I'll go 1, 2, and then maybe 3 tick marks. And then within each one, I'll draw a rectangle. So the way this will work is, if I look at where this first tick mark is, I'll draw up until I hit the curve here, and then up until I hit the curve above that. And then I'll use those as reference points for the height for the top of the rectangle, and then this one for the bottom of the rectangle. And then I'll form the rest of it. And then I do the same thing for these other tick marks. So I go up until I hit the curve, draw up until I hit the other curve, use that for the top of the rectangle, and then use this bottom point for the bottom of the rectangle. And then I just keep going like this. So this third tick mark point, there would be the bottom of the rectangle, go up until I hit this top curve, that would be the top of the rectangle, and I just keep going like that. So I'm not going to draw all the rectangles here, but somewhere down the road, I'm going to draw some arbitrary rectangle that will occur at this tick mark point, which I'll call x sub I. So from x sub I, I'm going to draw down until I hit the bottom curve, and up until I hit this top curve, and then give this rectangle a little bit of width. I'm going to draw this bottom part of it, a little bit of width there as well. Okay, so for this rectangle, this little bit of width, we're going to call this delta x, just like we did before when we did Riemann sums. And then for the height of this rectangle, well, the height of this rectangle depends on what the y value is at this point and what the y value is at this point down here. Specifically, I'm going to need to take that. I'm going to need to know f of x sub I, and then minus g of x sub I. In other words, I'll need to subtract those two y values, and when I do that, I will get this height. I will get the height of that rectangle. And once we know the base, delta x, and now I know this height, we can put that into a formula. So what I mean by that is we can start to write a formula for the area. So the area is going to be equal to, so one thing I know I'm going to need to do is I know I'm going to need to take a limit, just like we did before. That's going to let the number of rectangles go to infinity. I'm going to need a sigma notation from 1 to n. That means we're going to first sum the areas of n rectangles. So I equals 1 is just talking about the first rectangle. N is talking about the nth rectangle, the last rectangle. And then within this sigma, now I need to express the area of this arbitrary rectangle. Well, the height of that is f of xi minus g of xi. That is the height of that rectangle. Multiply it by the base for the width, delta x. Okay, so again, the thing within the sigma notation is the area of this arbitrary rectangle that I've drawn in orange. The sigma is going to add up the areas of n of these rectangles, and then the limit makes that approximation exact by letting us have an infinite number of rectangles. Alrighty, but we've seen limits like this before. We can write this as a definite integral. So we'll get the area equals, this will become an integral. My interval is from a to b. And what happens is this f of something minus g of something, that'll become just f of x minus g of x. And the delta x becomes sort of the dx in the integral form. And that is our formula for the area. So we've seen this before when we wrote out a limit of Riemann sum, and we defined what a definite integral was. Okay, so there's some notation I'm going to be using to talk about f of x and g of x when we do examples. I'm going to be calling f of x in this picture was the top function. So I'm going to call f of x y sub top sometimes, because it'll usually be in the form y equals some expression in terms of x. And g of x, I'll call this y sub bottom. It is the bottom function in this picture. All right, and this is our formula for the area between these two curves over the interval from a to b. All right, so I also want to just conceptually explain why this makes sense. So let's give a conceptual reason for this. So if I'm after finding the area between two functions f and g over some interval from a to b, and I'm just going to draw a picture one more time. So let's draw a picture, sort of a rough picture, and in this picture, let's just say that this is the curve f, and then I have another curve g, and just for simplicity, I'm going to draw both of them being above the x-axis, and I'm going to try to find the area between them on the interval from a to b. Okay, so the area between them over this interval from a to b. So we are after this shaded area here. So if I want to find that area, just looking at the picture, what I could do is I could first find the area between f and the x-axis. So this whole thing that I'm sort of tracing out in green here. So this will be equal to the area between f and the x-axis over that interval from a to b, but after I subtract something away. What I would need to subtract away is the area between g and the x-axis. I would need to subtract away this sort of like red dotted area that I'm drawing in here. So I need to subtract the area between g and the x-axis over that interval from a to b. But both of these areas we can express with an integral. This is the integral from a to b, because that's the interval of the function f of x dx. And then we'll have minus the integral from a to b of g of x dx. And we could combine these two integrals into one. This would be the integral from a to b of f of x minus g of x dx. And that's the formula that we had derived above, this formula over here. Okay, I'm actually changing that color to red there for that box just so it stands out a bit more. Okay, so I want to end this video with two notes about what we've just done. So the first is, when we apply this formula for the area between two curves, we're assuming that f of x is greater than or equal to the function g of x for all values of x on that interval. So that top function stays the top function the whole way on that interval. If it switches at some point and g of x becomes larger than f of x, then we have to be more careful when we compute the area. One important thing is when we compute this area between two curves, we want to count this as a positive area. So when we find the area between two curves, we always want it to count as positive. We never want it to count as negative. And the second note is this formula also works if f and g go below the x-axis. So in this conceptual explanation that we gave, for simplicity, I just said, oh, let me just draw it so that f and g were both above the x-axis. But this conceptual reason will also work if one of them or both of them go below the x-axis. So I would encourage you to think about why. But the way that we derived the formula in the beginning, using rectangles and the limit of the Riemann sum, that applies whether the functions are above the x-axis or below the x-axis just fine. But it's important, I think, to think about why this makes conceptual sense in the picture that I had drawn above, where we think about, oh, what happens if f and g might go below the x-axis. So in terms of our goals for this section, we have finished our first goal. We've derived a formula to get the area between two curves of the form y equals some stuff, and the other curve might also be y equals some stuff. In the next video, we will look at some examples.